Good afternoon. Today we're going to talk about circles, their circumference, and their area. Quick review of some basic terminology. We know that all circles have a center. That's what this guy is called. We know that all circles have a radius. That is the distance from the circle center to a point on the circle. And if you remember from when you were in elementary school, you learned that all circles have a diameter. The diameter is a chord that goes from one side of the circle to another and has to go through the center. We also have things like interior points. And we used those in Unit 9 when we talked about circles because often we had lines that were tangent to the circle from an exterior point. And we also have interior points. These are points that reside on the inside of the circle. Those are just some basic circle terms. If we look at a particular example of a circle, and if we remember the learning that we had in Unit 9, then we recognize that the name of this circle is Q. We name our circles by their center point. The radius in this circle could be QT. There's also another radius, QR. And we know that all radii of a circle will have the same measure, in this case, 16 meters. To find the length of the diameter of this circle, we need to remember that diameter is equal to 2 times our radius. In this case, our radius is 16. Our diameter then is 2 times 16, or 32 meters. And I went ahead and filled in what our interior points are. Those would be points that lie inside the circle, R, Q, and S, and an exterior point might be X. In converting from a radius to a diameter, there are 2 formulas that are handy to remember. The first is to find the diameter, and the diameter is always going to be 2 times the radius, as we spoke of above. Conversely, the radius can be of as being 1/2 of our diameter. Using these 2 conversions, we can go from a radius of 27 to get our diameter, giving us a radius of 54 inches. We can go backwards. If my diameter is 12x, then to find the radius, I'm going to take 1/2 of my diameter, in this case 12x, and that will give me a radius of 6x. 2 times 2.9 gives me a diameter of, wrong color, a diameter of 5.8. If you're following along with color, you're confused now, my apologies. And if I have a diameter of 18.6 centimeters, then I take 1/2 of that, and that will give me a radius, in this case, of 9.3. And that's how we can easily convert from radius to diameter. One of the essential questions we'd like to be able to answer in this section is how to find the area of a circle or various parts of a circle. To do that, I need to remember some of the formulas that we learned in our previous math careers. The circumference of a circle is always equal to 2 times pi times the radius, or the circumference can be thought of as pi times the diameter. Use whichever one works best with the information you're given. Lastly, we remember that the area of a circle can be found by taking the radius squared times pi. So let's do an example. If it were as simple as my just giving you the radius or the circumference, that would not be new learning as constituted by our being in geometry. So instead, we're going to ask you to discover what some of this information is. In this particular case, the 16 is pointing to a side of a right triangle. This is an inscribed right triangle. And I notice this chord, LJ, goes through center P, creating a semicircle. I also notice that there's a right angle here. And when given a right angle and the measure of two of its legs, I can use the Pythagorean theorem to find the length of the hypotenuse. The hypotenuse in this circle being the diameter. So I'm going to do that now. I'm going to remember that Pythagorean theorem says a squared plus b squared is equal to c squared. The two legs do not matter what order you write them in. And taking the sum of the square of those will give me my hypotenuse. In this case, 256 plus 900 equals c squared. That is 1156 on my handy dandy calculator. And that helps me learn that my diameter equals 34. And I note that in this case, this is my diameter. So to find my circumference, I can take the diameter times pi. And in our circle problems that involve pi, we always leave our answers in terms of pi. Anytime I substitute a decimal approximation for the pi symbol, I'm giving an approximate answer. The most precise and the exact answer will always involve the symbol pi. And then here I would put units. Circumference is a linear measure, so I do not need a square. To find my area, I'm going to use my area formula, pi times the radius squared. To find my radius, I need to take half of my diameter, half of 34, gives me a radius of 17. I can substitute that into my formula, and I learn that the area is equal to pi times the radius squared, or 289 pi. We typically put the pi symbol at the end of our expression. Area is always expressed in units squared. Let's look at another example. In example 4, we're asked to find the circumference and the area of this circle. To do so, I'm going to have to use the inscribed regular quadrilateral as shown. Because this shape is inscribed in my circle such that it creates right angles, then I know that if I look at this triangle specifically, it will create a 45-45 special right triangle. And if I remember the relationships between the sides of my special right triangles with 45-degree angles, I remember that each side is congruent and that the hypotenuse is equal to the side times the square root of 2. Therefore, I can conclude that in this case, the diameter of my circle is 7 square root 2. That helps me finding the circumference because I remember that circumference is really just diameter squared. Diameter times pi. So if my diameter is 7 square root 2 times pi, then I have my circumference. And again, we typically find the pi symbol written at the end of the expression. Finding our area, is a little bit more complicated. I remember that radius is equal to 1/2 of my diameter, or in this case, my radius is going to be equal to 1/2 of 7 square root 2, or 3.5 square root 2. To find the area, I'm going to use my area formula, pi times the radius squared. I'm going to substitute in the value of radius, which we said was 3.5 square root 2. I'm going to put that decimal there. And then I'm going to simplify this expression, remembering that I square my whole number. 12.25 is what I get when I square 3.5. And I have to also remember to square this radical, which gives me the whole number 2. When I simplify this, I end up with 24.5 pi units squared. That is my area. And I'm going to remember to label the units for it. The next example asks us to do something similar. In this particular example, I have an inscribed 30, 60, 90 right triangle. And if I remember again the relationships between the sides of a 30, 60, 90 right angle, I remember that the short leg can be expressed by x, the hypotenuse by 2x, which will turn out to be our diameter, and then the long leg of this triangle is equal to the expression x square root 3. By labeling my triangle, I'm given an equation that I can solve, which I'm going to do next. Finding the value of x will allow me to find the diameter of my circle. 9 square root 3 is equal to x square root 3. And when I simplify by dividing by the square root of 3 to isolate my variable, I learned that the short leg of this triangle is 9. My diameter is going to be equal to 2x, or 2 times 9, 18 units. Because I know my diameter, I can find my circumference. Circumference is my diameter times pi. So this becomes 18 pi units. To find my area, I'm going to need to use my area equation, pi times the radius squared. To find my radius, I take half of my diameter. I'll do that over here. Half of my diameter. My diameter was 18. When I take half of that, I end up with a radius of 9. To simplify this expression, I take 9 squared, which is 81, and I'm going to reverse these because we typically put pi at the end of our expressions. Multiplication is commutative and associative, so remember that the order that you multiply these does not matter. So now we have found the area and their circumference using two different kinds of special right triangles. For example 6, I have been given what we call a composite shape. I've been asked to find the area of the shaded region. To do that, I'm going to need to follow a couple of steps. My first step is to find the area of the entire shape, or the square. My second step will be to find the area of the non-shaded region, or the circle. And then finally, to find the area of just the shaded region, I'm going to subtract these two. I'm going to subtract the square minus the circle. And I remember that when you're doing subtraction, order matters. And I need to be careful with that. If I look at this problem, I see that the side of my square is 8. Because it's a square, each side is going to be 8. So the area of my square, which I'm going to indicate by putting a little square down here, is going to be found by doing side squared, or in this case, 8 squared, which gives me 64 units squared. So that's the area of my square. Now I have to find the area of my circle. To find the area of my circle, I'm going to use pi times the radius squared. My radius is half my diameter, so this distance is going to be 4 units. I will substitute that in here, and I learn that the area of my circle is 16 pi units squared. And then my third step, and I can even label these if it helps too. And then the third step is to subtract the two quantities. My square is 64 units squared, and my circle was 16 pi units squared. At this point, I need to determine, what am I saying here? At this point, this is my answer. If I look at 64 minus 16 pi, I recognize that these are not like terms and cannot be combined. I know that I need to leave my answer as an exact answer, so I'm not going to solve or simplify this by substituting in a value for pi. So my area for the shaded regions only is 64 minus 16 pi units squared. That looks a little strange, but it is an exact answer and exactly what we're looking for. Moving on to example 7, I'm going to find the area of the shaded region again, and we're going to follow that same strategy. I need to find the area of the circle, find the area of the inscribed triangle, and then I'll need to subtract the two. Finding the area of the circle is relatively easy. Finding the area of the triangle will involve some calculation. Let's start with step 1, which is finding the area of my circle. That can be found by taking area equals pi r squared. We are actually given the radius here. That's helpful. I'm going to substitute that in. And I end up with the area for my circle as being 100 pi units squared. Now, step 2 will be to find the area of my inscribed shape. To do this, I'm going to have to recognize that this is a regular triangle as indicated by having 3 congruent sides. Therefore, I'm going to use what we learned in the last lesson. I'm going to remember that the area formula I will likely need to use is area equals 1/2 times the perimeter times my apothem. To find my apothem, I'm going to solve the special 30, 60, 90 right triangle that is embedded in the larger polygon. I know that this is a 30, 60, 90 because equilateral angles are equal angular, and my radius splits this triangle angle into 2 equal pieces. The relationships on my 30, 60, 90 are x square root 3, and 2x. And when I label this picture with my given information, my radius being 10, then I can solve to find the apothem. If 2x is equal to 10, x is equal to 5, and I remember that that is my apothem. So now that I have my apothem, I can use that to substitute and find the distance from midpoint to the vertex. I take my 5, I substitute it in, and I learned that the side from the midpoint to the vertex is 5 square root 3, and I know that my whole side is double that, or 10 square root 3. That's helpful because I noticed that my formula requires me to find the perimeter. So I'm going to find the perimeter next. It's a triangle, so there are 3 sides, each being 10 square root 3, giving me a perimeter of 30 square root 3. I'm ready now to find the area of my triangle. 1/2 my perimeter times the apothem. My perimeter being 30 square root 3, and my apothem is 5. When I simplify this, I end up with an area of 75 square root 3 units squared for the area of my triangle. Now I have enough information to actually answer the question that's been asked. To find the area of just the shaded region, I will subtract these two quantities. My area of the shaded is equal to the area of my circle minus the area of my triangle. The area of my circle, we learned, was 100 pi, and the area of my triangle is 75 square root 3. And while that looks very strange for an area form calculation, that is the most exact answer. Remember, example answers are exact if I leave them in radical form and if I leave them in terms of pi. If that last example didn't make your head spin, this one surely will. I'm going to check my focus real quick just to make sure we can see clearly. To find the area of the region in example 8, I'm going to need to find the area of the circle and subtract the area of the trapping. Finding the area of my circle, step 1, is fairly simple because I was again given a diameter. I remember that the radius of my circle is half the diameter, so my radius is half of 12 or 6 units. So to find my area of my circle, I'm going to use pi times my radius squared, pi, substitute in 6, and come up with a calculation of 36 pi for the area of my circle. Again, that was the easy part. Step 2 is to find the area of the trapezoid. To do that, I'm going to remember that the area formula for a trapezoid is a little bit complicated. It's 1/2 the height times base 1 plus base 2. Fortunately, I've got some good information. I know base 1 and I know base 2. What I don't know is my height. I'll need to calculate that using the special right triangle that I see drawn here. I'm going to go ahead and draw that over here because it helps my brain. I know this is a 60-degree angle. And I know actually what this distance is. If I think about it, I can drop another perpendicular here, creating a rectangle. If this portion is 8 and the whole thing is 12, then I split my isosceles trapezoid base into components that are 2 units, 8 units, and 2 units. Hopefully that makes sense to you. That's helpful because I need to know what one side of that 30, 60, 90 right triangle is. And if I remember the relationships that occur inside a 30, 60, 90, I remember that across from the 30-degree angle is my short leg. Across from the 60-degree angle is a side that has a relationship of the short leg times the square root of 3, and that my hypotenuse is 2 times the short leg. I don't really need the hypotenuse in this particular case, but I do need to know what this long leg is, as it represents the height of my trapezoid. It's not a horrible calculation, x square root 3, and because I know that the short leg is 2, I can substitute that in, and I learn that the height of my trapezoid is 2 square root 3. And now I have all the components needed to find the area of this trapezoid. If I do that calculation, I'm going to do 1/2 of my height, which was 2 square root 3, times my bases. Base 1, 8, base 2 was 12. And now I can simplify this expression. Half of 2 is just 1. 8 plus 12 is 20. So I end up with 20 square root 3 as the area of my trapezoid. Finally, we're in a position where we can actually answer this question. 3, to find the area of the shaded region, I'm going to take the area of my circle minus the area of my trapezoid. And that will give me the area of my shaded region. Again, remember, order matters. You have to take the larger shape and subtract the smaller shape. In this particular case, the area of my circle is 36 pi units squared, and the area of my trapezoid is 20 square root 3 units squared. So the area of my shaded region can be represented by that expression. Well, example 8 was a lot of calculation. Example 9, oh, that says 8, is a little bit more straightforward. Again, we're finding the area of a composite shape. We're asked to find the shaded region. I notice in this case there are 3 shapes. There's the large circle and 2 smaller circles. My strategy in this case is going to be, first, find the area of the large circle. And second, I'm going to find the area of my smaller circles. And then finally, I'm going to subtract area of the big minus the combined area of the small. And that strategy should land me with the area of the shaded region. If you're looking at this, you will notice that finding the area of the 2 smaller circles is pretty straightforward because I was given the radius. If I look at my green circle, the smaller circle, and if I use pi radius squared, then I'm going to substitute in the radius of 3, and I come up with 9 pi as the area for this smallest circle. If I look at the next circle, I can use that same formula, area equals pi r squared. In this case, my radius is 10. And when I simplify that, I get 100 pi units squared. So the combined area for these 2 circles is going to be 109 pi units squared. That is what I will be subtracting from the larger circle. To find the area of the larger circle, I need to know the radius of the entire circle. Well, if we do some simple calculations here and think through it, I know that the diameter of this smallest circle is going to be the radius times 2. So this diameter is 6. And if I look at this larger circle here, I know that the diameter is equal to the radius times 2, which is 20. So then if I go to the large circle, its diameter is going to be equal to 20 plus 6, or 26. So the radius of this circle is half of the diameter, or 13 units. That allows me to find the area of my large circle. I'm going to take pi times my radius squared. And I simplify this and I get 169 pi units squared. Now I need to subtract these two quantities. And in doing so, I take the area of my large circle. Let me put a number 3 here so that we identify that this was step 1. These combined were step 2. Step 3 is to take the area of my big circle, which was 169 pi, and subtract from that the area of my smaller circles combined, and I end up with a final answer of 60, oh, good Lord, I can't subtract, 60 pi units squared. So as I said at the beginning, a little bit less aggressive than the previous examples. That is how we find the area of composite shapes and area of circles with inscribed triangles. Hope you enjoyed the lesson. We look forward to seeing you on the next one.